Hey guys, we're going to talk about Intro to Gases. This is the first page of our new unit on gases. This is page 32. So if you're at home and you don't already have the notes printed out and you are a person who prints out the notes, then go ahead and pause this video, go print them out, and then come back. All right, and again, if you don't have a printer, that's fine. You can just write on your own sheet of notebook paper best you can. Um, but uh, obviously printing's easier because you have all these words already there for you. But better than no notes, okay? All right, so what we're going to do first is talk about characteristics of gases. So this unit is all about gases, okay? So gases expand to fill any container. Expand. Okay? Gases are considered fluids, as are liquids, which means that the particles are not attracted to each other and they flow. Okay, gases can flow like liquids. Okay, gases have very low densities. Okay, and because there's a lot of empty space between the particles. Okay, so if this has some gas particles, there's a lot of empty space between those gas particles, right? And gases can be compressed. Compressed. Okay. They can be compressed. So if you have a gas in a container that's not rigid, you can compress it and make those particles close together. Whereas you can't really compress a liquid or a solid. It kind of is the volume that it is. Whereas gases, you can change their volume based on the size of their container. And gases undergo diffusion and effusion. Okay, what do those words mean? I think you've talked about diffusion in biology in terms of kind of what that means when you're doing diffusion across maybe like a membrane or something like that. When we're talking about gases in diffusion, we're talking about gases just like spreading out throughout a room, spreading out throughout a room or a container. Like if you think about if I were to take a can of like air freshener and spray it, it would expand across a room, right? It would stay highly concentrated right where you sprayed it at first, and then it would eventually like spread out throughout the room, right? So that's diffusion. Effusion is the movement of gas particles. Let's write this down. Movement of gas particles. Movement of gas particles. Movement of gas particles through a small opening. Through a small opening. So what does that mean? So if you have, again, if you think about like a can, like a spray can. I don't know how to draw like anything, guys. Here's a spray can, and here's a little nozzle that has a little hole in it where the gas particles are going to shoot through the little hole. That's effusion, the pressure of the gas particles being forced through that opening. That's effusion. Okay? Okay, let's talk about kinetic molecular theory. This is important. It sounds fancy, kinetic molecular theory, but it's really simple. So to make our lives easier, we make many assumptions about gases. So gases don't really behave ideally like we assume, but their behavior is close enough to being ideal that it usually doesn't matter. So what do I mean by ideally? So ideally, in most ideal situations, gases behave most like we predict that they will behave at low pressures and high temperatures, and when they are nonpolar atoms or molecules. Because if you remember, we talked about polarity. If you have atoms or molecules that are polar, they're going to be kind of attracted to each other, which kind of breaks some of these rules here. So gases don't always behave in these perfect situations, but it's close enough for all intents and purposes that it doesn't really matter, okay? So these are the 5 kind of rules of kinetic molecular theory. Again, kinetic molecular theory sounds fancy, but really, KMT, kinetic molecular theory, but really these are all very intuitive, okay? So it says particles in a gas are in constant random straight line motion, okay? Imagine these are gas particles. They're constantly moving. Most of the volume of a gas is empty space. So most of the stuff inside of this, even those gas particles in here, most of it's empty space in between the gas particles, okay? Number 3, there's no attraction or repulsion between the gas particles. So they're not attracted to each other, not repulsed by each other. They're just willy-nilly bouncing around, okay? Collisions between the gas particles are perfectly elastic. So that means that when two gas particles collide, they are just going to bounce off each other. They're not going to lose energy. They're not going to slow down. They're not going to speed up. They're just going to keep going. They're not attracted to each other. They're just going to bounce off the walls, bounce off each other, never losing energy. Okay, that's what perfectly elastic means. They're not going to lose energy. And here's an important one. The average kinetic energy, so that's kind of like saying the speed. It's kind of like saying how fast they're moving, is directly related to the temperature. Okay, so temperature goes up, particles move faster. Temperature goes down, particles move slower. That's all temperature is measuring. That's what temperature is measuring. Weird, right? Like, what is temperature? When we measure temperature, we're moving how fast particles are moving. Okay, so Kelvin. Do you guys remember learning about Kelvin? Kelvin. Kelvin is the absolute temperature scale. Whenever we're doing calculations with gases, our temperature needs to be in Kelvin. Always needs to be in Kelvin. So how do we convert Celsius? Well, you won't see anything in Fahrenheit in my class. I know it's weird because we use Fahrenheit in our everyday world as we're, checking the weather on our phone. But at least in America, in pretty much every other country, they use Celsius. But in chemistry class, you'll see everything in Celsius or Kelvin. If something is given to you in Celsius and it's a gas law or some sort of gas calculation, you need to convert it to Kelvin. And it's super easy. You just add 273 and then you're in Kelvin. That's it. Okay, so here's a practice problem. It says you have two 1-liter containers and each contain the same number of moles of nitrogen gas. Container A, so let's write this out. So we have container A and container B. They're both 1 liter, so that means they have the same volume, so they're going to be the same size. That's what volume is basically, is size of your container here. Pretend those are the same. Okay, so it says that they both have the same number of moles of nitrogen gas. So let's say they each have like 3 moles of nitrogen gas. I'm going to represent it with putting 3 dots in each. So container A is at a temperature of 273 Kelvin, and container B is at a temperature of 310 Kelvin. Okay, particles in which container have the most kinetic energy? Okay, so these guys are moving, like this. And whenever I draw a particle diagram like this, if I want to represent particles at a higher temperature or moving faster, I'm going to make longer arrows. So that's how I represent that. Okay. Okay, so particles in which container have the most kinetic energy? Obviously, container B, right? Container B. Particles in which container are moving fastest? Container B. Because the temperature is higher, and what does temperature measure? It measures kinetic energy, which means it's measuring how fast the particles are moving. Okay? All right. Oops. Okay, so pressure. The force that acts on a given area. Gases exert pressure on any surface they come in contact with. Okay, so what is pressure? So basically pressure measures the collisions. Collisions. Let's write that down. Collisions. That's basically what pressure is measuring, is how often are those particles colliding with the walls of their container. If they're colliding a lot, that's high pressure. If they're colliding not a lot, that's lower pressure. So more collisions equals more pressure. So whenever you're thinking about, is the pressure going to go up? Is the pressure going to go down? Think about what's going on with collisions. Are gas particles colliding with the walls of the container more often? Yes, then that's going to create more pressure, okay? So what are our units for pressure? Our units for pressure, let me scooch this down. All right, here, we have lots of different units for pressure to keep track of. Okay, we've got atmospheres, millimeters of mercury, torr, which, torr, and then, kPa and PSI. So this one goes, so millimeters of mercury and torr are the same thing. That's because there was a scientist named Torricelli who invented the barometer, which is what used millimeters of mercury. So that's why torr and millimeter, they kind of, named it after him. They kind of like, all right, let's make this a nickname torr. But now it's just confusing for students because it's really the same thing. The 101.325 goes with the kPa and then 14.1 psi. So all these are equal to each other. The one you'll see most often is probably ATM, which stands for atmospheres, okay? And, oh, this is a good point. Pressure decreases as you get further from sea level. What's sea level? Sea level is literally the level of the sea. So here I am, here's the ocean. All around the world, sea level is about the same. The pressure at sea level is about 1 atmosphere, okay? And then as you go up in elevation, the pressure decreases because there's more. Think about what are the air particles doing. If you have a person standing here, a magical person standing here on the beach, this person is standing on the ocean, pretend that's the beach. Standing here on the beach, there's going to be more air particles pushing down on him than somebody up here on the mountain. That's why people who climb Mount Everest, they need to bring oxygen with them. Often there's been some people that have done it without oxygen, but it's very dangerous. And if you get stranded up on Mount Everest, no one can come save you because there's no helicopters that can fly up there. There's not enough air for the helicopters to fly. There's just not a lot of air up here at Mount Everest. That's why it's a very dangerous hobby if you want to do that. But like for example, if you're down here, let's pretend this is Corpus Christi, right? If you guys have ever been to Corpus Christi, that is where you can go to the beach. It's at sea level, so it's about 760 millimeters of mercury, okay, or 760 torr, or 1 atmosphere, okay? And let's pretend this guy is up in Denver, Colorado, which is a little higher elevation. Denver, Colorado. This is the atmospheric pressure in Denver, Colorado is 615 millimeters of mercury, okay? So there's a little bit less air pressure up here. So that's why people who have a lot of lung problems, in like old people or people with emphysema or whatever, who have a lot of like lung problems, they often move to places like Florida and these places that are in, near sea level because there's more air to breathe there. It's easier on their lungs. Okay. Okay. What is this? Standard temperature and pressure. Standard temperature and pressure. What is standard temperature? Standard temperature is 0 degrees Celsius or 273 Kelvin. Standard pressure is these. So remember, these are all equal to each other. So the easiest one to remember is that it's 1 atmosphere and 273 Kelvin. Okay? Okay, so if I ever give you a problem and I said, hey, this gas was at standard temperature, you know it's at 273 Kelvin. Or if I say, hey, this is at STP, you know it's at 273 Kelvin and 1 atmosphere, or any combination of these, because these are all the same thing. Okay? Let's do an example. It says the pressure inside a submarine is 0.62 atmospheres. How much pressure is that in millimeters of mercury? Okay, well, we're just going to convert it. So 0.62 atmospheres. And if we know how many atmospheres are in a millimeter of mercury, then we can do that, right? Because we know that there's 1 atmosphere. I put atmospheres down here so that my units will cancel. In 760, because there's 1 atmosphere is equal to 760 millimeters of mercury. So when I put that in my calculator, I got 471.2 millimeters of mercury. Okay, that's it. Okay. Can you guys see that? Let me do a little zoom. I feel like it's kind of far away. Doop. There we go. Okay. Focus. There we go. All right, kilopascals. So it says how much is 0.62 atmospheres in kilopascals? kPa. So 0.62 atmospheres, and I want to go to kPa, and atmospheres goes down here, so it'll cancel out. Well, I know that 1 atmosphere is equal to 101.3 kPa. Okay, I put that in my calculator, and I get 62.8 kPa. Okay, so that's how you'd convert units. Okay. All right, let's take a look at the back of this, and then we'll be done. Oh, wrong one. This is what it should look like. Okay, on the back, I want to point out all these different relationships that exist. So I want to remind you guys that more collisions means more pressure, okay? More collisions means more pressure. So first thing we're going to talk about is pressure and volume. What's the relationship between pressure and volume? What will happen to pressure of a closed system if the volume decreases at a constant temperature? Okay, so let's say you have box A and box B. So let's say the volume decreases. So that means volume was big and now volume is small, meaning the container got smaller. And they're saying we're going to keep everything else constant. They're going to keep the temperature constant. This is a closed system, so it's implying that the number of particles is going to stay constant. Okay, so, and the temperature is constant, so the particles are just, I'm going to try to draw the same length of arrow to represent the particles aren't moving any faster. So what happened to the pressure? Volume went down, pressure went, well, the pressure went up, right? Because look, when the volume went down, now there's going to be a lot more collisions, right? There's going to be a lot more collisions going on here than there's going to be here. So this one's going to have a higher pressure, even though the volume is smaller. Okay, so pressure and volume are inversely related. They're inversely proportional. And that's what the graph would look like. That's what an inverse relationship looks like. Okay, as your volume goes up, your pressure goes down, and vice versa. So as a balloon rises in the air, does its volume increase, decrease, or remain the same? So as the balloon rises in the air, its volume is going to increase because the atmospheric pressure decreases, okay? Okay, let's talk about temperature and volume. Temperature and volume. What will happen to a volume of a closed system if the temperature is increased at a constant pressure? Okay, so let's say we want pressure to remain constant, meaning we want the collisions to remain constant. All right, so that means we kind of need and it's not a rigid container, so let's put it in like a balloon. So this is container A, container B. So I've got these particles. So if the temperature starts small, like that, and then what happens if we increase the temperature? What do you think will happen to that balloon? That balloon is going to expand, right? It's got to get bigger because the particles are moving faster, right? Okay. So volume and temperature are directly related. So if like temperature goes up, volume's also going to go up. Okay, if it's in a non-rigid container like a balloon, if the temperature increases, the volume's going to increase. That's why on like the side of those like hairspray cans and stuff, it's like, this is under pressure, don't expose it to a flame, or don't like expose it to very high temperatures because it could potentially explode. Okay? It says car tires that are not punctured, so a normal tire on your car is more likely to go flat in what season? Winter, guys. I just experienced this when I was driving during the snowstorm we had a couple weeks ago. I was driving my car and there was ice and snow everywhere. It was really scary. And then my car alerts me that my tire pressure is low, and that's because when it's cold outside, the gas particles move slower and there's less pressure in the car, in the tire. Okay, there's not as many collisions with the walls of the tire, so they're going to slow down, and the car tires are going to get a little bit deflated. Okay, and then once the temperature went up, that pressure sensor went away. It just magically was fixed. It's kind of cool. Okay, so temperature and pressure. What will happen to the pressure of a closed system if the temperature decreases at a constant volume? Okay, so if you have container A and container B, it doesn't say the volume changes. It says the volume is constant, so that means these containers are the same. And it's a closed system, so these are rigid containers, and they have the same number of particles. And says the temperature is going to decrease. So that implies that the temperature started out kind of hot, okay? And then it decreased. So now they're not moving as fast. Okay, so what happened to the pressure? Do you think the pressure, which one has more collisions? A would have more collisions. So when the temperature went down, it looks like the pressure also went down. Okay, so temperature goes down, pressure goes down. That's a direct relationship. When one goes down, the other goes down. When one goes up, the other goes up. So this is directly proportional. This one's directly proportional. So propane tanks have more pressure built up inside during what season? That would be summer. Summertime, there's going to be more pressure in your propane tank. Okay? Last one. Volume and number of moles. Number of moles. What will and we represent number of moles. You'll see this whole unit with a lowercase n. Okay. What will happen to the volume of a system if the number of moles is decreased at a constant pressure and temperature? Okay, so it's saying that the volume is going to change, so it can't be a rigid container. It's got to be something like a balloon again. So let's say we got a balloon like this, and this is A. Okay, and let's say we have like 4 gas particles inside of it, moving around, bouncing around, bounce, 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 bounce. Okay, and then it says, what happened to the volume of the system if the number of moles is decreased? So we have 4 moles in here. So let's let a little bit of the air out. If we let a little bit of the air out, let some of those moles of gas out, what's going to happen to the volume? It's going to get smaller, right? Ooh, it's going to deflate. Now we only have 2 moles of gas bouncing around. Okay, so that is the relationship between volume and number of moles. So if your number of moles goes down, your volume's going to go down, assuming all the other factors are constant. Now notice we've got volume, number of moles, temperature, pressure. Those are the big 4 variables we're dealing with when we're dealing with gas laws, okay? So those ones are directly proportional. As you blow more air into a beach ball, what happens to its size? It gets bigger, obviously. You put more air into it, it gets bigger. That's because you're adding more moles of gas in there, so its volume is going to increase. Okay, let me zoom out here for 1 second. I want to point something out. Oopsie. Okay, so here we have all of these. Okay, what do you notice? These are all directly proportional. This is the only one that's inverse. Okay, so the only one that's going to be inversely proportional is pressure and volume. The rest of them, directly proportional. Okay, okie dokie, go ahead and do the assignment.